Okay, time for another video presentation here. Today's topic is the Hooke's Law experiment, and this follows up on what you did in class, and it's a chance for you to check your results on the experiment. Now, if you remember from the experiment, we started off with a spring, and here I have set up the spring with the red marker at 0, and of course the idea is we're going to add masses onto the spring, which will stretch the spring. And when the spring stretches, then we were reading off the number of centimeters that the spring was stretching. So this is an idea of the experiment, which you probably remember, but it's a little bit complicated to try to figure out whether the results were right or not. And of course, another thing that's going to make it complicated is that not everybody's going to get the same results. Here I'm making up some sample numbers, and so I made some numbers up here for the centimeters, and of course that's the elongation, the stretching distance. One thing that we should all have exactly the same is the conversion from grams to kilograms. We did this for the weight mass activity and also for the finding mu activity, and since there are 1,000 grams for every 1 kilogram, the decimal place goes 3 places to the left. That's what happens when you divide by 1,000. So everybody should have the same column here for kilograms, 0.1, 0.15, 0.2, and 0.25. Well, you might be thinking, why? Why did we make that conversion from grams to kilograms? And the reason is, think about the force that's pulling down on the spring. You can see here the spring, by attaching a mass, the spring is stretching. But what is that force? That force is the weight. So weight is the force that's pulling down. In order to get weight, what we've been doing since for a while now is taking a mass in kilograms and multiplying it by 9.8. So that's how I got my numbers for the weight column over here. It was by taking the mass in kilograms and multiplying by 9.8. So we should all have the same values for the weight. You know, we might have rounded a little bit differently, but basically we should have the same values. The next thing that I wanted to do here is have the elongation in meters. So the elongation in meters, well, we had an elongation in centimeters. To get an elongation in meters, well, there's 100 centimeters for every meter, so you're dividing by 100. So when you divide by 100, basically the decimal place goes 2 places to the left. Now your numbers might be different than mine here for the elongation in centimeters. They probably are different, but the technique is the same, and we should all be moving the decimal place 2 places to the left to go from centimeters to meters. And that's what's going on over here. The next column that we had to fill out here is the constant, and that's the k in the F is equal to kx equation. So the constant in newtons divided by meters would be the force in newtons divided by the elongation in meters. So it's this column divided by this column. And I got some numbers over here which might be different than yours, but again, that's how I did it. I took the weight, which is the force in newtons, divided by the elongation in meters, and that's the x value in the F is equal to kx equation. And here's my constant. Your constant also was probably all around the same number. Might not have been around 12, it could have been around a different number, but all your numbers should be pretty close to each other here. Why wouldn't they be exact? Constant should stay constant. Well, that's because this is an experiment, right? So in the experiment, things could be off a little bit. All right, I have a title here of a force versus elongation graph, and people always wonder, or often wonder, which goes on the horizontal and which goes on the vertical. Well, it's always vertical versus horizontal. So on my graph here, I've got force on the vertical and elongation on the horizontal. And you should also on your correct solutions. The next thing we're going to do is try to put together a scale that will cover all of these things. And remember, the scales have to be equal increments. So I made a scale for elongation that went up in 0.05 increments, 0.05, 0.1, 0.15, and 0.2. And for the force, I needed to get up to 2.45, so I went up in half Newton increments. My next thing, of course, after that is to plot the points, and after I've plotted the points, I'm also drawing in a trend line. Okay, well, the questions on the back are basic graphing questions for the most part, but that should be the front of your paper. So hopefully you've used this as a good guide to check how you did on your experiment and filling out these answers. Hope that was helpful. If you still have questions, please ask me when we see each other the next time. And thanks for listening.